Hello, welcome again to the lecture series on automobile engineering. In this session, let us study about combustion in SI engines as well as in CI engines. Then how do we define combustion? So you can say relatively rapid chemical combination of hydrogen in the fuel with the oxygen in the air, resulting in a liberation of energy in the form of heat. Or you can simply say it is an exothermic chemical reaction often accompanied by a flame. Once you say exothermic, then the energy is released. In all combustion process, not necessarily we should have flame. But however, in IC engine, we will have a flame. So that is combustion. It is an exothermic reaction often accompanied by a flame. Combustion to occur, you require a combustible mixture. Let's say fuel and air. A combustible mixture is required in proper proportion. That is very important. In a proper proportion. Then after that, once you bring this fuel and air in contact, it will not ignite. So you require an ignition source. So if you have an ignition source, you can initiate combustion by giving out some energy to this fuel air mixture. So this fuel air mixture will get this energy, then prepare themselves for self ignition. Once then you got this source, you initiate combustion, then there should be a stabilization and propagation of flame. You should create conditions in such a way the flame should propagate with a particular speed, and as it travels it should consume the charge and continuously release the energy. So these are necessary for combustion of the fuel. So now in SI engine, the fuel that we use is C8H18. Okay. Now if I write this equation C8H18, then this is burned with oxygen. When I supply air, I cannot supply pure oxygen, so along with that I supply nitrogen. Then I am going to get carbon becomes carbon dioxide and hydrogen becomes water. Okay. So 8CO2, then 9H2O you get, and nitrogen is an inert gas, it should come out as it is. 8 plus 4.5 O2, so it is 12.5 O2. So for every 1 mole of oxygen I supply, oxygen and nitrogen by volume is 79/21. 79/21 it becomes something like 3.76. This value becomes 3.76. So I should write this one 12.5 into 3.76 of nitrogen I supply. Whatever nitrogen I supply, same thing comes out here. 12.5 into 3.76 of nitrogen comes out. Now if I say air fuel ratio, mass of air, that is 12.5 into 32 plus 3 mass of nitrogen, 12.5 into 3.76 into 28 molecular weight of nitrogen divided by mass of fuel, 12 into 8 carbon plus 1 into 18 hydrogen. So if I do this, so I might get approximately something like 50. That's what we call it as the air fuel ratio. Correct? So this ratio here, there is chemically completely balanced. This ratio you can call it as stoichiometric air fuel ratio. Stoichiometric air fuel ratio. So then we say 15 air, 1 fuel. Suppose it is 11:1, it is rich. 20:1, then it is lean. Okay, rich, this is lean. That's what we are talking right from the beginning. So here he had shown the real calculation is around 14.7 is the stoichiometric air fuel ratio. Okay, this is richer side, this is leaner side. So practical limit for carbureted engines. Okay, then ignition limit possibly for hydrocarbons is this 7 to 30. It is more than that, means it is too rich, too lean. Even if you pass a spark, it may not ignite. But this is the most of the time, this is what the operation range in an engine, air fuel ratio, or you can call them as ignition limits. So now you have the air fuel ratio, you have the mixture, you have the air, you have the fuel, you have studied about induction system, now you have studied about the fuel system, then you have studied about the ignition system. Let us pass the spark. Now what really happens? This has been explained. So if you look at for a petrol engine which works on Otto cycle, so there is, if this is PV, this is adiabatic compression, constant volume heat addition, then adiabatic expansion. This is what is shown: compression, constant volume heat addition, and expansion. This is basically very theoretical. In reality, you see here, this is the top dead center you have. This side you have the bottom dead center. The piston is moving from bottom dead center towards the top dead center. Okay, reaches to your top dead center, then it is expanded. You are not ignited or anything like that. That is what you call it as a motoring curve. In reality, in petrol engine, around 20 degrees before the top dead center, we pass a spark. Moment you pass a spark, ignition will not happen. A flame front will appear, bubble of flame at B. It's around 20, around 12 degree here. This is what we call it as ignition lag, first stage of combustion. Here a flame will appear like this. Now here there was a spark. After ignition lag, small flame front will appear. Assume here you are having mixture, air fuel mixture in proper proportion you have. This flame front will travel like this and start consuming the charge. As it starts consuming the charge, you can see the pressure increases. The pressure reaches to a maximum value around 11 degree after the tap dead center. This we call it as flame propagation stage. Flame travels. Then the piston moves downwards. On the piston this high pressure will be applied. If you see this view, so the piston is here and it is going downwards. Now these gases exert pressure on this and it will generate the power. As it goes down, you see here it expands and the remaining air fuel mixture, whatever it is, fuel is there, that will burn out and release the energy. But a large amount of energy, more than around 70% of the energy gets released by this point and the remaining energy gets released over here. This is what we call it as the stages of combustion in SI engine. So whether we should have a larger ignition lag, whether it should travel, make the flame travel faster. If the flame does not travel fast, what happens? If the ignition lag is very small, what happens? If the ignition lag increases, what happens? Which are the factors responsible for these things? Let us look at those. Fuel quality, the effect of engine variables on ignition lag. Fuel quality is one of them. Fuel quality is one of them. Fuel quality matters a lot. For example, octane has a longer ignition, whereas normal heptane has a very small ignition lag. So it depends on the fuel quality is connected with ignition lag. Mixture strength, suppose you know what is air fuel ratio now. You know what is stoichiometric air fuel ratio. Slightly rich mixture has lower ignition lag compared to lean mixture. Not very rich, I'm talking about slightly, maybe 10% or 15% more. Rich mixture has lower ignition lag compared to lean mixture. High initial temperature and pressure of the mixture, also high compression, compression ratio, which will increase the temperature and pressure of the mixture, leads to low ignition lag. However, engine turbulence, which is connected with the engine speed, does not affect ignition lag. So later you understand the importance of ignition lag. So it is necessary in petrol engine. We should have a reasonable ignition lag. Otherwise, it leads to abnormal combustion, which I'll be discussing little later. So if the ignition lag, you want to increase ignition lag to avoid abnormal combustion, then it is necessary for us to reduce the compression ratio of the engine. If you reduce the compression ratio of the engine, then the thermal efficiency of the engine will come down. So thus there are many repercussions of this. Then we require a reasonably good flame speed. Tell you why we require a reasonably good flame speed. You imagine this is the top view of the combustion chamber. Imagine that I have the spark plug here. I have located the spark plug here. And here we have the air fuel mixture. Fine. Okay. So now I pass the spark. After the ignition lag, a small flame front will appear. Small flame front will appear. Then what happens is this grows like this and start traveling with certain speed. This is what I call it as V flame speed. As it travels, it consumes the charge and pressure rise will increase. Like, it's like this is what happens. So you have seen, you have passed the spark. Here the flame front will appear. Then the pressure rise. Correct. This is what really happens as it travels and travels. Flame front has a very high temperature at the order of something like 2800 to 3000 Kelvin. And this will be radiating continuously the heat. That's one part. Second thing is, here you are burned gases. So the volume increases, and because of that it starts expanding. It will compress this charge. This is what I call it as end charge. This end charge is receiving the heat because of this and also getting compressed. And there is a chance that end charge might auto-ignite. So we should not give a chance for the end charge to auto-ignite. That means the flame should travel very fast and consume before it prepares itself for auto-ignition. That's where the flame spray propagation is important. Definitely that will help in even sizing of the engine cylinder, or how to increase this flame speed is very important. So slightly rich mixture enhance flame speed. If you have high compression ratio, high mixture temperature and pressure and enhances flame speed. That is also there. If the intake temperature and pressure increases intake, flame speed. But note that in the meantime, these factors reduce the ignition lag too. That is a problem. So if you have more engine load, with increase in engine load, the cycle pressure increase, hence the flame speed increases. Turbulence increases flame speed. Engine load increases, engine speed increases, engine size may decrease the flame speed. So this is the problem. If you want to increase the flame speed, that may even somewhat increase the auto ignition to happen and all that. So this is where exactly the difficulty is. Okay, now as I said, next what happens? I explained with this figure. If this flame front develops like this and smoothly consumes the charge, this is your combustion curve. Absolutely no problem. But by chance, the end charge auto ignites. There is burning from this side and burning from this side. There will be a pressure rise so that it will set up a pressure wave. That's what we call it as knocking. This is what we call it as abnormal combustion. The engine is knocking, you'll get the hammering sound. Right? This is what happens. Okay. So because of this detonate, sometimes it is called detonation. This makes the engine run noisy and roughness, and it will also create mechanical damage. Please know that if you have the engine on the piston, continuously a varying pressure is acting. Because of that, that varying pressure is also acting on the crankshaft. That leads to vibrations. Another thing is, you see here, there is a lot of temperature increase. There will be temperature wave also. Whatever lubrication is here, that lubricant will be burnt out. And once the lubricant is not completely burnt, what will happen? It will leave some kind of carbon deposits. Carbon deposits. These carbon deposits later start acting as spark plugs. That means before, in the next cycle, before passing the spark, this may ignite the air fuel charge. And another thing is, the temperature pressure is so high, so uneven expansion of the piston takes place and piston seizure may occur. It leads to complete damage of the engine. So that is what the danger is. So that's why we have to carefully design our engine parameters to avoid abnormal combustion. Okay, this is what exactly I was talking about. So, CI engine, please note that whole challenge is here. Efficiency of an engine depends upon compression ratio. If I increase the compression ratio, it may lead to, in SI engine, some kind of abnormal combustion beyond certain value. How to design engine so that I use optimum compression ratio, so the efficiency is optimized and still normal combustion happens. This is what the present day engine management systems are trying to do. Right? Let us talk about CI engine. Again, if I start calculating diesel as a hydrocarbon, so let me go backwards quite far. No worry. Because I want to tell you how to trace the points, like where to go. Okay, now hold on. I want to just go to the fuel portion. If you see here, diesel fuel, the formula is C12H24. Diesel, the fuel formula is C8H8E. So let us go back to this point. C12H24. Okay, this is the formula of the diesel. Oh, okay. Now for this also we can calculate the air fuel ratio. C12H24, again oxygen, again nitrogen, then again you can calculate CO2, then this will become H2O, then nitrogen. So 24 H2O, 12 I can write here, 12 CO2, 12 and 6 of this, 18 O2, 18 into 3.76, then you can find out what should be the air fuel ratio. So 18 into 32 plus 18, 3.76, 18 into 3.76 into 28 divided by 8 into 12, sorry, 12 into 12 plus 1 into 24. You can find this stoichiometric air fuel ratio. So that will be 18 into 32 plus 18 to 3.76 into 28 is equal to something like 2471. Divided by 12 into 12 must be 144 plus 24, that is 168. So 2471 divided by 168 is around 14.7. That's the kind of air fuel ratio you get with the CNG. But normally we never operate at the stoichiometric air condition of 14.7:1. The diesel engine beauty is that it operates between 20:1 to 100:1, always on the leaner side. Okay, so power output, air fuel ratio, you can see here. Power output is high, but you'll get smoke 10:18. As the air fuel ratio increases, power output decreases, but to be more cleaner. Okay, so now let us understand how exactly the combustion happens. So let me tell you one very interesting thing about diesel engine is you have air, fine. Okay, into this air I am injecting fuel. Injecting fuel. Only certain region I try to keep stoichiometric condition. All other place it is the linear condition. So once we ignite this, then the flame spreads. So that is what happens. During the suction stroke, air is sucked in, compressed. At the end of compression stroke, we are spraying fuel. And at certain position, we maintain stoichiometric air fuel ratio. At all other places, it's very, very lean. Overall air fuel ratio becomes very, very lean. So this is what is happening here. So first of all, you are compressing the air. Pen color, ink color, yes. You are compressing here like this. You are injecting the fuel. A flame front will appear here. This is what we call it as ignition delay. In petrol engine we call it as ignition lag. Here we call it as ignition delay. What happens once the injector start injecting, it continue to inject up till here. So a large amount of fuel gets accumulated in one region. Of course, here also you'll have this, but large accumulated. Somewhere at this point, a flame front will appear. When the flame front appears, it finds a large amount of fuel around it and it consumes very fast. Because of that, what happens? There is a sudden pressure increase. That's what happens. Then, if you continue to inject the fuel, right, then the flame front will travel and consume the charge. So this is what you can call it as controlled combustion. A large amount of energy gets released, then this is what we call it as after combustion. Ignition delay, what you can call it as uncontrolled combustion, because I've already injected the fuel, I have no hold on that. Then you have controlled combustion, then you call it as after burning. During this stage, too much of fuel has accumulated, then it may simply set a pressure wave. That is what we call it as diesel knock. Okay, because of that, the engine will start running rough. If the engine is mounted on the vehicle, then the vehicle will subject it to unnecessary vibrations. So what is that we have to do is, we should not allow too much of fuel to get accumulated. That means to say, we should see to that ignition delay is as short as possible. So we have to identify the factors which influences this ignition delay and reduce that ignition delay. As I explained in the previous video, in the present day common rail injection system, that's what we have done. We have introduced the pilot injection system. Only inject a very small quantity of fuel, stop it till that fuel get ignited and flame front appears. After that you start injecting so that the combustion will be very, very smooth. That's what we are doing. Okay, so that's what the stages are. So we need to reduce the delay. If you want to start explaining the delay, then there is what you can call it as physical delay and then chemical delay. Physical delay is about atomization, mixing, vaporization, then mixing, forming a proper mixture. Then attaining ignition temperature is what we call it as chemical delay. Okay, so these things, right? What are the factors which affect these? Okay, chemical delay, I think it is difficult. The type of quality of the fuel, that is very important. If you have C10, it's very good. In the meantime, alpha methyl naphthalene, if you take, that has a very large ignition delay. This is a very short ignition delay. So fuel quality matters. Size of the droplet matters better. You should have smaller size. Vaporization will be faster. For that you need higher injection pressure. That's why nowadays common rail injection, we use the pressure of the order of 1600 plus bar, and size of the droplet is very, very small. Okay, injection advance angle, no. Here though low pressure, low temperature and all that, sometimes it will definitely increase the ignition delay. But better to have very good compression ratio, high compression ratios. But already we are using high compression ratios in the order of 20 to 24. If I further increase the compression ratio, then to withstand very high pressure, the piston has to be made strong. The piston has to be made strong, then the piston weight will increase, the weight of the reciprocating mass will increase, the engine speed start decreasing, like because of the inertia. These kind of difficulties we have to find out some right compression ratio so that the ignition delay is smaller. Increase the intake temperature, definitely it will improve, but it will affect the volumetric efficiency. That is there. Jacket water temperature will improve the ignition delay, means decrease the ignition delay. Fuel temperature will increase the intake pressure and supercharging. Yes, all this will definitely improve this speed. Okay, so that we can optimize the parameters so that the ignition delay is minimum. Air fuel ratio. Okay, that is also going to the rate affected by the maximum. With increase in load, air fuel ratio decreases, operating temperature and hence delay period decreases. Engine size, no, it will not help much. Okay, type of combustion chamber, yes, help a lot. So that is where we have direct combustion, direct injection and IDI type, indirect injection. So create lot of turbulence, definitely it will reduce the physical delay. That way it will help. So here I have listed out what are the variables which can affect the ignition delay so that diesel knock can be reduced and we can make the engine run very smooth. So the difference between petrol knock and diesel knock is that petrol knock happens because of shorter ignition lag. During the end of combustion, during third phase it happens, during afterburning stage. If I maintain larger ignition delay, this is what happens in diesel engine. It happens in the beginning of the combustion itself. Anyway, by introducing now electronics, that is common rail injection, here introducing engine management system and petrol injection, we are smoothing out all these things and improving the combustion processes. Okay, how do we introduce diesel knock? All those parameters I've already discussed, the parameters, engine parameters which affect the ignition delay. By controlling this, it is possible to improve that. So there are lots of videos available on this. You can have a look at them. But the whole summary, what I would like to say is that I wanted to make it very clear to everyone what are the stoichiometric air fuel ratio that we use in petrol engine, stoichiometric air fuel ratio that we use in diesel engine. They are almost the same. Second, what are the ignition limits? That is, in petrol engine, the ignition limits is something like, you can say approximately 10:1 to 20:1. And most of the times the petrol engine runs on the richer side. So I can call it as a correct air fuel ratio is around 14.7:1. In diesel engine, the beauty is, even though the air fuel ratio is 14.7:1, most of the times it runs on the leaner side, that is 20:1 to 100:1. That's the beauty of this. In the petrol engine, what you call it as, there is knocking. Knocking is because of low ignition lag of the fuel. So because of that, we cannot increase the compression ratio. But how to carefully develop new methods like petrol injection system, still increasing the compression ratio, because compression ratio affects the efficiency of the engine. It is always better to use higher compression ratio so that the thermal efficiency will be better. So these are the points we discussed. That here in petrol engine, yes, diesel engine, if I increase the compression ratio, it is always better. Already we are using a compression ratio of 20 to 24. If you further increase the compression ratio, definitely to withstand high pressure, I think we have to make the piston much stronger and the cylinder stronger, leading to heavy reciprocating parts that will lead to inertia, that lead to low engine speeds. That's another kind of problem. So we have to find a media for this. That's where the common rail injection system that we are using and atomizing the fuel to at very high pressure, reducing the physical delay. Also somehow, ignition chemical delay, we do not have much of a control, reducing a lot of physical delay in that, and so that we are reducing the ignition delay and trying to avoid the diesel knock. And by avoiding the diesel knock, eliminating the diesel knock, we are making the diesel engine run very smooth, and so that the vehicle runs very smooth. So these are some of the points that I wanted to make clear to you. Hope you understand these things correct, and quite often in between I have already discussed these points. With this, let us end up the unit number 4. Thank you very much.